Hi, Miss Venable here, bringing you a screencastify on catalysts and inhibitors. So we have been studying chemical reactions, and one of the things we've discussed are rates. Some reactions are very, very fast, and some reactions are very, very slow, and some are in between. And there are factors that affect the rate of reactions. So let's go over a couple of those before we get started. The first factor is the nature of the reactants. Maybe they're just more naturally chemically reactive. We know that some things are. So maybe the reaction goes fast because the reactants are just very reactive. Okay, that's the first and biggest and most obvious factor. Another factor is temperature. So this kind of goes back to collision theory. Collision theory says that in order for chemical reactions to happen, the reactants have to have collisions. And so the particles, the substances have to collide at the right orientation. And this is important, they have to have enough energy when they collide. And so they can either be moving fast enough, they have to be going fast enough, or they have to be vibrating quickly enough. So they think about energy in terms of like a kinetic energy, like speed or motion. And this is why temperature is one of the big factors. So if they have higher temperature, then they're moving faster. So it's more likely that a collision will result in an effective reaction. And the more effective reactions you have, the faster the rate of your reaction will go overall. Another factor, and this one is really more for gases, is pressure. And so, and this goes along with concentration of the reactants. If you pack in more particles closer together by increasing concentration, or if it's a gas by increasing pressure, you're pushing the particles more closely together. This means they're more likely to collide. So you're going to have just a greater number of collisions in order to make your reaction go. And that means your reaction is going to go faster. Now, the last big factor is the one we're going to talk about in this presentation, which is presence of a catalyst or an inhibitor. And catalysts and inhibitors are sort of flip coin, opposite sides of the same coin. Catalysts, when you add them to a chemical reaction, they tend to speed up the chemical reaction, and inhibitors tend to slow down the chemical reaction. So we have gone over the factors that affect the rates of chemical reactions. So let's look at our objectives. Objective 1, we want to describe the role of catalysts and how they're useful in things like industry. We're going to describe the chemical changes that can occur because of catalysts. We're going to explain how catalysts and inhibitors affect reaction rates, going over the collision theory. And we're going to describe the role of inhibitors as biological enzymes, food preservatives, or coatings for metals to prevent tarnishing or rusting. So let's talk about catalysts in the paper industry, which is a huge industry. We all use paper products every day in lots of ways we don't even think about. So take just a minute and think. Just take a guess. How much paper do you think you use in a year? And if you're American, the answer might surprise you. Where do you think paper comes from? And how does paper go from being brown, like a paper bag is brown, to being white, like the paper that we write on, or paper towels or toilet paper that we use in the bathroom? How does it go from being brown to white? So you can pause the video and have a discussion about that. And we're going to move on. So how much paper do you use in a year? Well, if you're an American, an average person American, in a year, you're going to use 700 pounds. That is a lot. 40% of the paper worldwide is used by Americans, even though we're only 5% of the world population. So like a lot of things, folks in America are using kind of more than our fair share. If you want to learn more about paper usage and how it affects our environment, check out the link I gave you in the Google Slides. It's called Facts About Paper. Question 2, where does paper come from? Paper comes from wood. And we know that the logging industry, or the cutting down of trees, has been a big environmental concern in recent years because we need the trees to remove carbon dioxide and prevent the greenhouse effect from accelerating. But when we need to paper, more and more demand for paper, we're cutting more and more trees. Luckily, we can replant them. They are a renewable resource. So the process to turn wood into paper is pretty involved. Of course, you have to log the trees. You have to debark them. You have to send them to a paper mill where the trees are cut and they're turned into pulp, which is kind of like mush, like sawdust kind of pulp. Water has to be added, and then they have to introduce chemicals to bleach out the color. And we're going to talk about that in a second. And then last, they have to dry out the pulp in big sheets, form it into rolls, and then cut it into whatever product or paper supplies that you're going to buy. Okay, question 3. I mentioned this already. How does paper go from being brown to white? And the answer is bleaching. So the most common bleach that we use on our clothes and cleaning is chlorine bleach, but there are other bleaching agents like sodium borohydride, sodium sulfite. The most common bleaching agent that is used in the paper industry is actually hydrogen peroxide. Same thing that you use on your cuts, just a lot more concentrated. And the way it works is it works on something in the paper called the lignin. The lignin, or lignin, not sure the pronunciation on that, is the substance in the pulp that gives the paper the brown color. So if you can remove the lignin out of the paper, it will turn white. And the way they do that is by oxidizing the lignin using a bleaching agent. Otherwise, they kind of remove some electrons out of the bleaching or out of the lignin, and that turns it into a colorless color. Instead of being brown, it becomes colorless, and then your paper is going to look white. So if we weren't using any sort of catalyst, and we were just using the hydrogen peroxide as a bleaching agent, it would take weeks or months, okay, to convince all of that lignin to give up its electrons so that it would turn colorless. Obviously, in industry, we want to make money. Time is essential. We don't want to wait weeks or months to bleach out our paper. We want to put the chemicals on it and be done. So chemists add a catalyst. Okay, a catalyst is something that's going to speed up the rate of the bleaching process. And in this case, the catalyst that they use is called dinuclear trium oxybriggan manganese complex. We'll never say that again. We're going to call it manganese 4 oxide, or another name for it would be manganese dioxide. A lot easier to say. The actual pathway that it goes through has a bunch of steps. I haven't counted those, but I think it's about like 14 steps or something in there. And that's going to be lots of energy exchanges. Electrons are transferring, bonds are being broken, new bonds are forming. So there's a long process. We're just going to shortcut that longer process and write the simple chemical equation just showing the before and the after. So what we have before is hydrogen peroxide on the left side of this chemical equation here. And the chemical formula for that is H2O2. That's hydrogen peroxide. And then the products are here on the right-hand side. So we're going to have water, H2O, and oxygen, O2. And that's why when you put peroxide on a cut, you always see bubbles, because that's the oxygen being released. Your blood is kind of acting like a catalyst. So what is the catalyst? Well, the catalyst isn't written in as part of the equation because it's really not a reactant. It's really not a product. It's kind of temporarily a reactant, but then you get it back. So it doesn't end up really being a reactant. So what we do with the catalyst is we always write it over the yield arrow. So MnO2 is the catalyst here written over the yield. And the important thing to understand about a catalyst is that it provides an alternate pathway. It doesn't change the starting or the ending chemicals, but what it does is it lowers the amount of energy the reactants have to absorb out of the environment for them to obtain the kind of state in which they're ready to actually react. And that state is called the activated complex. When the compounds have the right amount of energy and they're in the right orientation and they're ready to react. That's called the activated complex. So your reactants always have to absorb some energy out of the environment in order to reach that state, and that's called the activation energy. And what the catalyst does is it basically lowers the activation energy. So the amount of energy in the activated complex isn't as much. It doesn't need to be as much. So like all reactants, Hydrogen peroxide will reach this state called the activated complex in order to have sufficient energy to react. So what does collision theory say about this? Well, collision theory says that in order to react, that reactants have to collide in the correct orientation with sufficient energy. And so when the hydrogen peroxide molecules collide with each other, they have to be going fast enough. And the catalyst helps with this by lowering the necessary amount of energy. It makes the reactions that do, the collisions that do occur, it makes them much more effective or productive or more likely to form the products. Okay, we're going to look at a graph in just a second. It kind of looks like this. But before we do, I want to teach you guys some of the symbols you're going to see on the graph. So the first symbol is EA, E subscript A. That stands for activation energy. That's the energy necessary to reach the activated complex at the top. Delta H is the overall change in energy if we compare reactants and products. And we'll calculate it from some y-axis values, the final and the initial heat. If your delta H value is negative, then your reaction is called exothermic. And that means that overall energy gets released. The reactants have more energy stored in the chemical bonds than the products need in their chemical bonds. And so that excess, when you form the products, that excess energy that was stored in the reactants bonds gets released to the air. So there's going to be less stored potential energy in the bonds in the products. And what that means is that when you touch it or feel it, it might feel warm or hot to you if that energy is released as heat. You might see it as light if you see flames or sparks, or perhaps you'll hear a fizz or a pop and it's releasing energy as sound, but it has to release energy overall. If your delta H value is a positive, that means that your reaction is endothermic. And that means that the reactants are absorbing energy out of the environment to get started. The activation energy, they all have to do that. But then they keep absorbing because the products they're trying to form need bonds that are storing more energy than the reactants originally have. So that the reactants have to draw energy out of the air around them or the container that they're in. This means that the products have more stored potential energy than the reactants had originally. So if you touch this or feel this container, it's going to pull energy out of your hands. So your hands are going to feel cold or cool. Okay, now that you know what all those terms are, we can take a look at the graph. So here on the left-hand side are my reactants, H2O2. Here on the right-hand side are my products, water and oxygen. And basically the curve shows the progress of the reaction. On the y-axis, we have the amount of energy that's stored in the bonds here. And I see that the starting energy for my hydrogen peroxide is 300 kilojoules. Kilojoules is the energy unit. And so I've labeled that here as HI, or initial heat. The final heat is HF, and I see that that is 100 kilojoules here. I also see there are two humps. There is a hump, the brown hump here is for the uncatalyzed reaction, and the very top of that hump would be what we call the activated complex, when the reactants have absorbed enough energy so that the reaction can progress on its own. And so this arrow pointing up, this brown arrow, is going to be the EA, or activation energy, that's necessary to achieve the activated complex so that the reaction can happen. If I catalyze it, notice the hump is lower. So the activated complex is down here at 450 kilojoules, and there's a lot less activation energy required for my reactants to get started. So let's answer these questions. Number one, what's the activation energy without a catalyst? So we're going to be looking at the brown line here. The starting energy for my reactants is 300 kilojoules. The necessary energy at the activated complex is 650 kilojoules, which means my reactants are going to have to gain 350 kilojoules to get to the top. So number one is 350 kilojoules. Number two is not going to be as much, because when you catalyze a reaction, it doesn't need as much activation energy. So let's take a look at that. If we have a catalyzed reaction, then my activated complex is up here, and that's going to require 450 kilojoules. Again, my reactants start out with 300 kilojoules. So to get up to 450, they're only going to have to gain 150 kilojoules. So the activation energy with a catalyst would be 150 kilojoules. Number three, what is the heat of reaction? So heat of reaction is, we don't care about what happened in the middle. All we look at is starting and ending energy levels. So my starting energy is 300. My ending energy for my products is 100. And then the change in the heat or enthalpy is just the difference. And you always subtract the final minus the initial. So my final is always the products, that's 100. And my initial is the reactants here, and that's 300. So 100 minus 300 would be negative 200. And the negative sign is important. You have to put it in there. So the answer number 3 is negative 200 kilojoules. Number 4, is it exothermic or endothermic? Okay, well, like I mentioned over here, if your delta H value is negative, then the reaction is exothermic. So you just have to remember that or memorize negative enthalpies means exothermic. If you touch it, how would it feel? If I go back and over here and look, if I have an exothermic reaction, it's going to release energy as heat, light, or sound. So if you feel it, it might feel warm to you. Alrighty, so this was the potential energy graph for the decomposition of hydrogen peroxide with the manganese dioxide catalyst. Okay, let's take a look at inhibitors. So remember, catalysts and inhibitors are sort of flip sides of the same coin. So a catalyst is going to lower activation energy and make a reaction rate go faster. An inhibitor does the exact opposite. It raises activation energy so that the reaction rate goes more slowly. So their role is kind of to slow down chemical reactions by increasing activation energy. They work in different ways. There's lots of different kinds of inhibitors. We're not going to study inhibitors too much in this high school level chemistry class, but if you do take like an organic chemistry class, you'll get much more into inhibitors. There are lots of inhibitors that are in our bodies, and they play very vital roles. But I'm just going to give you a few examples, okay? Food preservatives. Where would we be in modern life if we couldn't preserve food, right? We'd have to eat everything fresh immediately. We'd have to go ahead and kill it and eat it, or it would rot. So food preservatives are really important because they inhibit bacterial growth, and they do it by either dehydrating or directly attacking microbes that would be growing on the food. Pharmaceutical drugs, where would we be without modern medicine? Okay, most of them are enzyme inhibitors. So they're going to take something like you have biological enzymes, which are sort of like catalysts, and what these inhibitors are going to do is get in the way. They basically get in the way of the uptake of certain chemicals in your body. They block or alter the active site on the enzyme. Okay, coatings. We don't ever think about, hey, it's coated. Well, if we didn't have coatings on metals, they would all tarnish and rust, like almost, over time. And they do this by eliminating the access to oxygen and water. So coatings or surface agents that we put on things are a very important inhibitor. Let's look at a potential energy graph for an inhibitor. It is sort of the opposite of a catalyst. So a catalyst would lower the activation energy. What an inhibitor does is it raises it. So I've done the inhibitor here in green. And let's go through the same set of questions here. Number 1, what's the activation energy without an inhibitor? So again, that's the brown one, and that hasn't changed. So the reactants still have 300, and then they require an additional 350 to get to the activated complex here at 650. So number 1 is 350 kilojoules, just like before. Number 2, what's the activation energy with an inhibitor? Now remember, last time, our activation energy was less when we had a catalyst. So let's see what it is now. Okay, with an inhibitor, I have to get up to the activated complex at the top of the green hump, which is 700 kilojoules. My reactants already have 300 kilojoules. So the activation energy would be how much energy the reactants have to gain. So 700 minus 300 would be 400 kilojoules. So number 2, the activation energy with an inhibitor is 400 kilojoules. Number 3, the heat of reaction is also changed. So again, I just look at where I ended, where I started, just read the y-axis. So my final heat for the products here is 450. My initial heat for the reactants here is 300. So I'm going to subtract final minus initial, and I end up with positive 150 this time. And the positive sign means endothermic. So if you feel it, it's going to feel cold. It's going to be pulling energy out of your hands. So conclusions, catalysts and inhibitors both affect reaction rates, very necessary in everyday life. For more information, check out the Chem for Kids website linked in your Google Slides. This is Ms. Venable. Thanks for watching Catalysts and Inhibitors.